Hi everyone, welcome back to Math 261. This is Scott. Let's get started. On the docket right now is section 1.3, which is about what are called vector equations. And what we're going to be doing in this section, and the next section, section 1.4 as well, is we're going to be taking what we explored in the first two sections, section 1.1 and 1.2, which had to do with systems of linear equations, and we're going to look at how to apply the same techniques and the same ideas from those sections to some apparently different, but actually the same situations. So the first of those apparently different situations is vector equations, which are equations involving vectors. So let's first define what we mean by that. So a column vector or just vector is, for this class and for our purposes, we can think of it as a matrix that consists of just one column. A matrix with only one column. So then the notation here. So the notation that we're going to use, so this is the notation that we'll use in this class. There are other kinds of notation that are commonly used in other contexts, but let me just say how we're going to be writing these things. So first off, Rn. This represents the set of all n-dimensional column vectors. So these are n-dimensional column vectors. So R as in the real numbers with a power of n. So then also A, B, C, etc. So these represent vectors, and you indicate the difference between a vector and a number by putting a little notch above it. It's like a half arrow. So these represent vectors. So the little arrow up top makes it a vector. Now books. So textbooks typically will not put any kind of marking on the letter. What they will use instead is just a bold typeface for a vector, as opposed to an italic typeface if it's representing just a scalar. So books use bold typeface and no arrow. Also, you should know that that in physics, it's also very common to indicate these by underlining rather than a mark above. So rather than a macron above it, they mark it with an underlining. So physicists often underline vectors. Okay, so then if we want to indicate that a certain vector has a certain dimension, belongs to a certain piece of a column space, then what we can say is we can write something like V, which is also a commonly used vector letter because the vector starts with V. So we write V belongs to Rn, that's what that means, belongs to, or is an element of. It's a Greek letter epsilon, short for element. So we write this to mean that V has n entries. Alright, and so then, just so that we're all on the same page here, examples of things we could say. We could have for R2 and R3 will be the ones that we will frequently default to because those are the ones that we're most familiar with from most of the geometric sides of things. So R2, we can have things like U, which equals something like 1, 2. V could equal something like 0, 3. W could equal -2, 1, things like that. For example. And R3. R3 just is like these, except instead of having 2 rows, they have three rows. So we could have a U, which is equal to 0, 1, 1. We could have a V, which is equal to 3, 2, 1. We could have a W, which equals 0, 0, 5, for example. So these are just to show you what these things look like and how we'll be writing them. So other notations are common, so note. Other notations are also common. We won't use them so often in this class, but you should know that they exist. So for example, let's say we had 1, 2. So 1, 2, for example, can also be written as, and one common way of writing it would be with angle brackets. So 1, 2, or another way of writing it would be using the i's and j's. So 1i plus 2j, for example. So these would be the two most common other ways of writing two-dimensional vectors, and the three-dimensional vectors would be the same. You would just include another entry here, and you would include a k here. But these are not notations that we will frequently use. We'll occasionally make use of them here and there, but they won't be our main notation. Our main notation will be as column vectors. Now let's discuss some of the things that can be done with vectors which relate to the arithmetic that we're more familiar with in the case of just numbers. So vector arithmetic. So two vectors of the same dimension So two vectors of the same dimension can be added. And we just add it component-wise. So you just add it component by component. So for example, let's say that we have u as a vector. Let's say it's 1, 2, 3. Let's say we have v as a vector, and it's negative 1, 0, and 2, let's say. Then u plus v would just be what you would expect, which is just taking the entries of u, the entries of v, adding them each together. So u plus v would then equal just 1 plus negative 1, 2 plus 0, 3 plus 2. So in other words, just 0, 2, and 5. So they can be, so any two vectors, as long as they belong to the same dimension, they can be added together, and it just goes as we would expect. And any vector can also be multiplied by a scalar. So scalar multiplication, this refers to multiplying a vector by just a real number, which we will call a scalar for this purpose, and it's called that because it scales the vector up or down. So we can multiply, or in other words, scale a vector by a real number, which in this context we would call a scalar because it's what we're scaling by. So for example, let's say that u was equal to 1, 2, 3. And let's say that c, which would be a common letter we might use for a scalar, c for constant. You notice it does not have an arrow above it because it is not a vector, it is merely a scalar. Let's say that's equal to 2, then cu, which we can also write as 2 in front of 1, 2, and 3. And what we just do is we just multiply each of the entries of the vector by that scalar. 2 times 1, 2 times 2, 2 times 3. So it just kind of distributes its way in. And that gives us, of course, 2, 4, and 6. So it has just been scaled up by a factor of 2. That's why we call it scalar multiplication. And then what would arithmetic be without certain fundamental constants of nature? And the most important constant of nature when it comes to ordinary arithmetic is 0, and that is in turn what is one of the most important constants when it comes to vectors. So the 0 vectors. The 0 vector, one for each dimension. And we don't usually indicate the dimension if it is clear, but we will just write 0 with a little line, with a little vector arrow above it, and this is equal to the column of all zeros, and this will be whatever dimension we need it to be to match the other vectors that we're talking about. So in rows. And we will not usually make much of the indication of which 0 vector it is. Different 0 vectors will have different numbers. So for R2, for example, 0 vector would be 0, 0 for R3. We'd have a 0 vector with 3 zeros, etc. And it'll be clear from the context which 0 vector we're talking about in most cases. And if it's not, then it can be clear. All right, so those are the three components of vector arithmetic. We can have addition, scalar multiplication, and then there's this constant, which is the 0 vector. Now, because all the arithmetic is done on a component by component basis, what that means is that the properties that we know from ordinary real number arithmetic will all translate pretty nicely into the properties of vector arithmetic. So everything we thought we knew about arithmetic will largely still be true in the case of vector arithmetic. So we refer to these as the algebraic properties of Rn. So the setup here, for any u, v, and w belonging to Rn, and any c and d which are scalars, so we can just say just real numbers, so in other words scalars, then the following are all true. So that's the setup. Then the following will always be true. And here, what we're actually just really doing, so you don't have to memorize these, you don't have to memorize which property says which thing, but what we're going to be doing here is essentially just giving ourselves permission to do the arithmetic that we know and love in the vector realm as well as in the just classic real number realm. So okay, here are the things we know. Well, we know that addition among ordinary numbers is commutative, meaning you can add in either direction, and that's true here too. So u plus v is the same as v plus u. Doesn't matter if you add from the left or add from the right, adding is adding. Same thing, we know that that addition among real numbers is associative, as they say, which means that if I did u plus v, and then I added the result to w, that's the same thing as if I had done it in the other order, where I had added v plus w, and then I had added the result to u. So those are the same thing, and they're the same in real number addition, and they're the same in vector addition. Now, neither of these two properties is true about, say, subtraction, but they are true about addition, and that's a fact for real numbers, and it's a fact for vectors. All right, now we said that 0 had was an important constant. And the thing that makes 0 0 is the fact that if you add it to any vector, just like if you add the number 0 to any number, then it doesn't matter which side you add it from. In either case, you just end up doing nothing. You end up not changing the number at all. And another important thing about 0 is that it's what you get when you cancel. When you cancel a number with its opposite, or the same thing is true if you were to cancel a vector with the opposite vector. By opposite, what we mean is u has its opposite, which is negative u, and what this actually represents is -1 scalar multiple of u. And then we have a fifth property here, which is that we have distributive pieces for the scalar multiplication. So if I were to do c, the scalar, times u plus v, that's the same as just cu plus cv. So it distributes in. But there's another way in this case that distribution can also be framed. So we could also think of it as being a matter of c plus d, so two scalars, added together and then multiplied by u, which is the same as cu plus du. And then more to know is that scalar multiplication is also associative, and it's associative in this sense. So if I did c times du, that's the same as cd times u. And the last one, I know it's a little boring to write down things that you would have never even considered being false because you're so accustomed to real number arithmetic, but we're on some shaky ground when we move from what is a familiar space to a less familiar space, and we want to make sure that the things that we know in the one space will still be true in the other. And that's what we're just doing here, is giving ourselves permission to do most of the arithmetic that we would ordinarily do. And from now on, we're not going to really appeal to this very often again. We're just going to say that that if it feels right, it's probably true for this vector arithmetic. We'll see other cases where that's not the case, but here, as long as we're just talking about vectors, scalar multiplication, things like that, if it feels good, it's probably okay. If it is something that you can do with numbers, it's probably something you can do with vectors. The important thing is we are not defining vector multiplication. We're not defining in this section any way that you can multiply a vector by another vector. That is not our concern here. We are just adding vectors together or multiplying vectors by scalars. That's all. Okay. So that is just us giving ourselves permission to do what we would have done by instinct anyway. Now we can put the pieces of vector arithmetic together in a more complicated way, and those are what are called linear combinations. So this is putting together scalar multiplication along with vector addition. So given several vectors all of the same dimension, so we'll write them like this: v1, v2, dot dot dot, up to vp. And these are all in Rn. So in other words, what we're saying is, i.e. So this is just mathese for saying we have p different vectors, each of dimension n. P vectors, each of dimension n. And C1, C2, up to CP, so in other words, also, and these are all in R, so i.e. the same number of scalars as we have vectors, then a linear combination of the V, so the V1 through VP, is anything of the form, and we can call it Y, is equal to, and now here's the form, C1 V1 plus C2 V2 dot 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 up to CP VP. So in other words, we take scalar multiples of each of our vectors and we add the results together, and what we get is what's called a linear combination. So, i.e., multiply the vectors by the scalars and add the results. The C's here are called weights. The C1 up through CP are called weights. Each one is the weight of its corresponding vector. Alright. Now finally, at long last, after 3 pages and a half hour of notes, we can actually define the thing that this section is supposed to be about, and that is vector equations. So, now, a vector equation So a vector equation is any equation of the form, and then how it looks is this. We will have x1, not a vector, just a scalar x1, a1, the vector, plus x2, a2, plus dot dot dot, plus up to xp, ap, and this is all going to equal the vector b, where the x's, x1 up through xp, are unknown scalars. The a1 up through ap and b all belong to Rn. So what this has to do with anything that we've talked about previously in this course, in other words, sections 1.1 and 1.2, is the following. So the connection. Connection to 1.1 and 1.2 is that we can think of the x's as still being the variables. So the x1 up through xp are p variables. The a1 up through AP are column vectors that represent the n coefficients of the variables in each of the n equations. So in other words, so i.e. let's just say ai, some generic I, this represents the n coefficients of xi. This gives the coefficients of xi. And then b, this b is a column vector B is a column vector that gives the constant term. The constant terms of the n equations. Now, if we wanted to rewrite this as an augmented coefficient matrix, this would look like this. So we would have the A1, we would have the A2, and here what we're doing is we're applying some notation where when we write a matrix and then we write a column vector inside it, that means this column represents A1. And then we have the P, and then we are augmenting it with the B. So these column vectors are the columns of the matrix. Okay. So what this means is that a vector equation is actually the same thing as the system of linear equations that we were dealing with before. And similarly to that situation, we can create an augmented matrix out of them. Now, let's discuss something more vector specific, and that is a span. So this is a topic we'll return to many times throughout this course, but this is going to be our first taste of it. So span. The span of a collection of vectors is the set that is made up of all linear combinations of those vectors. So in other words, and we write it like this, span, and then squiggly brackets, like for a set brace, V1 up through VP. This is equal to this, so the span of this gives the complete set of possible vectors that are made via C1 V1 plus dot 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 CP VP for any combination of scalars C1 up through CP. So I can make any element of the span of a collection of vectors by just choosing out of thin air all the vectors that I want, all the weights that I want to apply to each one. So let's say I had 5 vectors in my set here. I could just then choose 5 different scalars, and I would multiply the first by the first vector, the second by the second vector, the third by the third vector, the fourth by the fourth vector, the fifth by the fifth vector, add them all up, and what I would get would be in the span. And anybody else who chose any other 5 scalars would also produce an element of the span, and together all possible choices make up the complete set of the span of those vectors. So geometrically, let's talk about spans of collections. So let's say we have a span of 1 non-zero vector. So if we have just one non-zero vector, and let's just for the sake of being clear, let's just pretend like we're talking about R3, because that's the easiest one to imagine. So R2 and R3 are the easiest ones to imagine. So what we're talking about is a 3-dimensional space, X, Y, Z, each pointing their different direction. We're talking about something like the very room you are in, where you give 3 coordinates for every point. And then let's say that we have one random vector pointing off some direction, let's call it V. Now, what it means to have a linear combination of the vector V when there's only one of them is basically we can just apply whatever weight we want. So that means we can scale it up, we can scale it down. So then the span of V would be the line through the origin that contains the vector, in other words, the arrow, represented by V. So what that means is that little dotted line up there is the span of V. Now, if we have the span of two non-zero vectors, again, in R3, we're talking about within R3, then what we're talking about is two different directions pointing out of the origin, and together we can always make a plane out of them. So span of u v will be a plane that goes through the origin and contains both u and v. So in other words, we've got two different directions pointing somewhere in space, and then the span is basically it is the plane, like the two-dimensional sheet that contains both of those. And then as a diagram, it's a diagram here, so graphically, what this could look like is, let's say what we've got are the three dimensions pointing in the direction of the x-axis, the y-axis, and the z-axis. And let's say we've got two vectors. One of them, I'm going to draw them kind of short and small because this is very difficult. So let's say u goes that way, and in particular, let's say v goes that way. Now, all the linear combinations of them, but it's easier to specify those directions if we go like that. But anyway, so then the okay, so there's v going that way, and let's say that u is like so. Okay, so then that's a u, that's a v. I know it's not a very clear, easy to see picture. I'll show you a better one in a second, one done not by me. But then all of the linear combinations will be basically the little plane that you make by drawing all of the parallel versions of u and v all throughout the plane. Parallel to u, to that one, parallel to that one, parallel to that one, parallel to that one, and so on. And again, this is not a very easy thing to draw in 2 dimensions, so it does tend to tax our abilities. But just to give you a general picture once again of what's going on, imagine like right here, say in space is the origin. We have one direction pointing out that way, one direction pointing out that way. Then the plane that contains both of those directions, that will be the span of those 2 vectors. And to show you another example here, so this is from the paper version of your textbook. There will be similar figures in the section 1.3 of your online version. But if you look in here, so this is a span of a single vector. We have our 3 coordinate axes. They were just oriented in space. Got a vector coming out of the origin there, and then the line that contains that vector, that will be the span of a single vector. Whereas if we have 2 different vectors, say v going out that way, u going out that way, the span will be the sheet, like the plane that contains both of those directions through the origin. And now finally, the last part of this particular section is going to be an actual task that we will master, and that is the task of determining whether a given vector is in a given span. Alright, so here's the setup. So we'll have a collection of vectors and we can call them A1, A2, etc. up to AP, and they'll all be in some Rn. So they'll all be of a certain dimension. And then, and B also in Rn. So then we'll have some other vector. And the question will be, question, is B in an element of the span of the A's, A1, up through AP? Alright, so let's try to figure out what this question would be asking. So it's saying we have a bunch of vectors, we have a different vector. Is this different vector in the span of the first vectors? Now, what that means is it a linear combination of those other ones? If it is, then that means there is some collection of weights that we could find that would make it equal that. So in other words, is B a linear combination the AI. By the way, whenever we're referring to a collection of them, one way we could do it is just by using a generic index such as I in order to avoid having to write out A1 through AP every time. So is there a combination of weights C1 up through CP so that C1 A1 plus dot 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 CP AP ends up equaling B. In other words, is there a solution to the vector equation x1 a1 plus dot 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 plus till we get to the last one, which is xp AP equals B, which finally then, according to what we've been saying before, is saying is the system, is the linear system with augmented coefficient matrix A1 up to AP augmented by B consistent. And then finally, that gives us one more way of wording it. When we row reduce, do we get 0, 0, 0, 0 followed by something that's not 0? And here I mean just a number B, meaning one of the elements of the rows here. So that's what this is all about. It's all about row reducing. And you'll find that for the first portion of this course, we may disguise things in various amounts of crazy new language, but what we often can do is figure out a way to turn the problem into a problem of row reduction. Let's see what this would look like as an example. And let's see, so let's say A1 equals 1, 3, and 2. Let's say A2 equals 2, 1, and 4. And let's say finally B is equal to -1, -8, 5. And the question is B in span of A1 and A2? So an hour ago, you would have thought that this question was nonsense. But now, you realize this question is actually just a new version of a question we've asked before, which is whether if you set up something like this, the augmented matrix, that looks like so, whether under these circumstances we will end up row reducing ourselves into a telltale sign of inconsistency. Namely, do we end up with a row that's all zeros until the augmented side, at which point it is non-zero? Well, to answer this question, what we want to do is we want to do whatever row reduction we can to try to get this into RREF form. And I like the pivot we've already got for the first row, so we'll use that to clear out all the things below it. So row 2 is getting replaced by -3 times row 1 plus old row 2. And while we're at it, let's do a similar thing to row 3, only now it's going to be -2 times row 1 plus old row 3. And we'll see what we get. Okay, so now 1, 2, -1. Nothing changes about the first row. That's the one that we're using to clear out the other ones. Now it's going to be -3 times this plus this. So it's going to make a 0. That was the whole point. And now -3 times 2 is -6, plus 5 or plus 1 is -5. -3 times 1 is +3, plus -8 is -5. And then the next row, 0. -2 times 2 is going to make -4, that makes it 0. -2 times -1 is +2, plus 5 makes a 7. And here, what we've got is a telltale sign that the system is inconsistent. Inconsistent system. So B is not in the span of A1 and A2. Now, what it would have looked like if it had been, so if it had been in the span, what that would have caused to happen here would be a 0 down here instead of a 7. And so let's call this actually retroactively example A, and that would have led to a different conclusion. Let's see, B is, and now let's take -1, -8, and then -2 in the span of those two vectors, A1 and A2. So now let's hit the reset. Try this again with a new third column in our matrix. Three, 1, -8, and 2, 4, -2 this time. Now we would do the same two row operations that we did before, but now the conclusion would be a little different. So the same two row operations, so we won't write them all out again, but it all goes very similarly until the very last entry. -5, -5, then 0, 0, and 0. So far we are seeing not the signs of a of an inconsistent system. And in fact, actually here we can see that there are going to be pivots in every row, or sorry, in every column, which means then we have no no loss here. Every column gets itself pivoted, and so we end up with a nice and consistent system with a unique solution, in fact. And here we can just seal the deal by taking rows 2 and scaling it by -1/5. And what's that going to give us? 1, 2, -1, 0, 1, 1, 0, 0, 0. Which is all looking pretty good. We can now clear out the entry above that by taking row 1 and replacing it by -2 times row 2 plus old row 1. And that'll give us, so now 1, that'll clear that. -2 times this is going to be -2 plus -1 is -3. And now 0, 1, 1, 0, 0, 0. And here, what that means then is this is consistent, and in fact we even found a solution, so this is consistent. This is consistent, which means that this new vector, -1, -8, -2, is in span of A1 and A2. In particular, we would have solutions. The unique solution x1 equals -3 and x2 equals 1 implies that -3 times A1 plus 1 times A2 is equal to the vector in question, which was, what was it again? -1, -8, -2. And we can check. We can check that by going -3 times A1, which was 214, plus 1 times, sorry, this one was 132. Here, let's start that over again. Scratch that. So -3 times 132 plus 1 times, that's the 214, which equals, or does it, -1, -8, and -2. So we got -6. Oh, sorry. Let's just do this nice and easy. So -3 plus 2. -9 plus 1. -6 plus 4. -1, -8, -2. Looks good to me. Looks like it checks. So that's what it means. The question, is this or is this not in the span of these other vectors? It means can weights be found to make it a linear combination of those other vectors? And that is the same as trying to solve for those weights. If it turns out that such a system cannot be solved, is inconsistent in other words, then what that means is that it is not in the span. If conversely it is possible to solve it, then that means that it is in the span. Alright, well that about does it for section 1.3. Join me next time for the next installment of Math 261. Till then, bye!